This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to cover polyprotic acids and buffers. A buffer is a solution that is a mix of a weak acid and its conjugate base. But the conjugate base is usually going to come from a source other than the weak acid itself. So let's look at these two examples to illustrate exactly what that means. In this first example, we just have the simple combination of acetic acid and water. And acetic acid is a weak acid. In the last video, we went over how to solve weak acid problems, and that was with the ICE table. So if you need more information on that, go watch the last video. But for the ICE table, remember you just start with your original amount of your acid, which we got from the problem, and then you have to do minus and plus X to figure out exactly how much there would be of your products and reactants at equilibrium. Eventually, you would get to this part where you're using the Ka to find the hydrogen concentration, which would be equal to X from your ICE table. And remember that X is also equal to the amount of conjugate base that was created due to your original acid losing its hydrogen. And because this is a weak acid, X is a really small value, so the amount of conjugate base that we have is really, really small. After the dissociation of the acetic acid in the solution, we pretty much still have about 0.01 moles of acetic acid, and then a way, way smaller amount of the conjugate base. So we have much more of our acid than we do of the conjugate base. And to create an effective buffer, you're going to need fairly similar amounts of your conjugate base and the weak acid. So to effectively do this, you need to have another source contribute to that concentration of your conjugate base. And that's what we have in the problem on the right. So on the right side, we have the same amount of our weak acid, 0.01 moles. And we've also added sodium acetate. And sodium acetate is Na, and then the formula for acetate. And notice that that is an ionic compound. So the positive charge of the sodium is what allows it to form a salt with the acetate ion, and acetate is the name for the conjugate base of acetic acid. And from our solubility video, we went over the fact that compounds that have group 1 metals are going to be completely soluble in solution. So all of the sodium and all of the acetate are going to dissociate from each other. So if we have a concentration of 0.01 molar of sodium acetate, then that means that we basically have a concentration of 0.01 molar for just acetate, and then the sodium is going to dissociate from the acetate and then just kind of be on its own, so we can just completely ignore the sodium here. And that's basically going to be the only way, or the main way, that you're going to see conjugate buffers added. They're going to be combined with a group 1 metal a lot of the time, so when they get added to the solution, the cation just dissolves, and then you're left with the anion conjugate base. From here, you may be tempted to do something like an ICE table and do minus X and then plus X for your products. And what you're going to end up with would be a fairly complicated ICE table that has multiple values that are adding or subtracting X. And what you do instead is use the Henderson Haselbach equation, which is really just a shortcut that takes all of this math and simplifies it into a really simple equation, which is pH equals pKa. So that would be the pKa of acetic acid plus the log of the concentration of the conjugate base over the concentration of the acid. And again, if you were to work through this ICE table, you could probably figure it out eventually, but the Henderson Haselbach just takes all that math and makes it way, way more simple. And then for the concentration of your conjugate base, you're just going to plug in the concentration that you calculated of the base whenever you use the salt from which the base came from. And then the concentration of the acid is just the original concentration that was given to you in the problem. And you may be wondering, why are these concentrations the same, and why haven't they reacted in a way that has changed their concentrations? And the reason is that because it's a weak acid and the conjugate base is also weak, the change in those concentrations, so the plus and minus X, would be a really, really small change. So the total values are basically the same. You're basically, even after equilibrium is reached, you're still going to have about 0.01 moles of your acid and about 0.01 moles of your conjugate base. The whole point of making a buffer is because they are used to resist changes in pH. So if you add hydrogen, the conjugate base should combine with the hydrogen to negate that effect. And then if you add OH, then the acid part of it should combine with the OH to negate the effect of adding the hydroxide ions. And an effective buffer, the acid that is used to make the buffer has a pKa that is within 1 of the desired pH of the solution. Let's look at the example we were just working on to see why the pKa needs to be within 1 of the pH. So for acetic acid, the pKa is 4.76. So acetic acid would only be an effective buffer for solutions with a pH that would be between 5.76 and 3.76. So what that means is that the log term in the Henderson Haselbach equation can equal -1 or +1, and we would still have an effective buffer. So then ask yourself, log of what equals -1 and log of what equals +1? So to solve that log, you do 10 to the 1 equals x, and then on the right, 10 to the -1 equals x. So for the log term to equal 1, what is inside the parentheses must be equal to 10. And then for the log term to equal -1, whatever's inside the parentheses must be equal to 10 to the -1, which would be 0.1. And remember that what is inside the parentheses is the ratio of the concentration of the conjugate base over the concentration of the acid. So for that ratio to equal 10, what that means is that we would have 10 times more of our conjugate base than our acid. And then if that equaled 0.1, then that means that we have 10 times more of the denominator, which would be the acid, compared to our conjugate base. So to have an effective buffer, your conjugate base and acid need to be within a magnitude of 10 of one another. Now we'll look at polyprotic acids, and there's really nothing new about polyprotic acids in terms of the foundations of acids and bases. So what we're going to do is pretty much just apply what we already know about acids and bases to a polyprotic acid. We have two polyprotic acids here. The one on top is a weak acid, and then the one on bottom is a strong acid. So we're looking at the weak acid first. In this weak acid, a concept you need to understand that is the first hydrogen, if that is weakly acidic, then it's pretty much the only hydrogen that's going to dissociate. For our first acid, we have a Ka of 7.1 times 10 to the -3, which makes this a weak acid. And for any weak acid, you're going to solve this by using an ice table. And we're not actually going to solve this, but remember that the change is -x and then +x for the products. And your final value for the conjugate base will always be x. And then for H3O+, that's also going to be x. And if that doesn't make sense to you, then go back and watch the weak acid video. So if you're ever asked to calculate the pH of a polyprotic acid and it's a weak acid, just do your ice table and then you would be done. Now you may be wondering, well, what happens to the hydrogens from the H2PO4 that can further dissociate? And if you're thinking that, that's a really good thought, but the reason that we don't count those is because the Ka of H2PO4 is so small that any additional dissociation is going to be negligible compared to the value of x that we got from the dissociation of the first acid. So yes, some percentage of H2PO4 is going to dissociate, but it's not going to contribute enough H3O that we need to consider it in our calculations for the pH of the solution. Now let's look at our strong acid. In the strong acid, this time we are going to have a significant amount of dissociation of multiple hydrogens. So H2SO4 is a strong acid. So that means that all of H2SO4 is going to dissociate into the conjugate base HSO4 and H3O. So the amount of H3O+ will be equal to however much H2SO4 that we started with. So let's say we started with 0.1 molarity of H2SO4. Then after time is allowed for the acid to dissociate, we will have none of that left. All of it will have turned into HSO4- and H3O+. So now we need to consider how much of HSO4- is going to dissociate. And if you look at the Ka for HSO4-, it's actually fairly significant. So to figure out how much additional H3O is going to be created from your HSO4-, you would do an ice table, because HSO4- is a weak acid, but it's not so weak that it's not going to contribute a significant amount of H3O+. So it's strong enough that enough is going to dissociate that we need to figure out how much more H3O plus is going to be created. And the key distinction between when you need to consider this option is that you started off with a strong acid in H2SO4, where the first acid that we worked with was a weak acid. So only that first proton is going to dissociate at any significant amount. And in reality, these types of problems are not really going to come up. It's more about the thought process behind this is a really good way to challenge yourself to make sure that you're really strong on acids and bases, because acids and bases are some of the most high yield topics on the entire test. The next thing we need to look at is how you would make a buffer whenever you're using a polyprotic acid and how you choose the correct acid and conjugate base pairing. Remember that to create an effective buffer, your pKa needs to be within 1 of the pH. So in most problems, they're going to tell you the desired pH of a buffer, and then you need to figure out how do you create that buffer. Let's say that they tell you the desired pH is 6.2. The first thing you need to do is figure out which one of your pKa's is closest to 6.2. And clearly that is going to be the 7.2 pKa for the dissociation of the second hydrogen off of our acid. So that means that the acid in our buffer is going to be H2PO4 and the base will be HPO4 2-. So you set this up by using the Henderson Haselbach equation. So you would do 6.2 because that's the desired pH equals the pKa of the acid, so 7.2, and then plus the log of the concentration of your base over your acid. So we end up with -1 equals log, and I'm just going to put x, and remember that x is equal to that ratio. So that means that 10 to the -1 equals x, so that would give us x equals 0.1. So then to create a buffer that has a pH of 6.2, and we are using this acid and this base, we need the ratio within these parentheses to equal 0.1, which means that we need 10 times more of the acid than we do of the conjugate base. The final thing we're going to look at is how we can change the protonation levels of acids and bases by changing the pH of the solution that they are in. So previously, we've pretty much only looked at how putting an acid or base into a solution changes the pH. What we're going to look at now is a situation where we are controlling and fixing the pH at a certain level, and then we're seeing how does that affect the protonation of our acids and bases. So for example, a situation that we could do right now is if we create a solution where we keep the pH at 1, and then we add this acid in there, and we're specifically looking for what would happen to the hydrogens that are connected to that molecule. Your two rules are that if the pH is less than the pKa, then that species will be protonated. In other words, the hydrogen will not be away from the molecule. The hydrogen will stay attached to the molecule. And that is because pH, if we are ensuring that the pH remains low, that means that we have a very high concentration of H+. And so if we have a high concentration of H+, then it just makes it easier for all of those hydrogens to stay connected to that molecule. And that kind of relates to Le Chatelier's principle. Conversely, if the pH is more than the pKa, that indicates a low hydrogen concentration, which then makes it easier for our molecules to be deprotonated. So back to our example of a pH of 1. If we have a pH of 1, 1 is less than every single pKa for that acid, so our molecule would be fully protonated. Now if we pick another pH, let's say pH of 9, that pH is more than our first pKa, and it's more than the second pKa. So that means that one hydrogen is going to pop off because it's more than 2.4, and then a second hydrogen is going to leave because the pH is more than 7.2. So then our molecule at a pH of 9 would only have one hydrogen left. So then our molecule would be HPO4 2-. This is applied most commonly to amino acids. And here we have a picture of a fully protonated amino acid. So an amino acid has 3 hydrogens that could possibly leave. And notice what the pKa's are for each one of those hydrogens. So now ask yourself, what pH would we need for each one of those hydrogens to remain on the amino acid? So your pH would need to be less than the lowest pKa, which is 2.16. So to keep this protonated, our pH would have to be less than 2.16. So when you're dealing with charged amino acids, they are always implying a physiological pH, and physiological pH is around 7.3. So then you need to ask yourself, what pKa's is that greater than? What pKa's is that less than? So 7.3 is greater than 4.15 and 2.16. So when the pH is greater than the pKa, then those become deprotonated. So those no longer have the hydrogens on them, which would give each one of those oxygens a negative charge. But that pH is less than 9.58, which would mean that that one remains protonated. So it keeps that positive charge. So that is why certain amino acids have certain charges. It has to do with the relationships between pH and pKa. So if we were to add up all the charges for this amino acid, we would end up with a total net charge of -1. This is a super, super important concept, so make sure that you are really good on determining if something is protonated or deprotonated. And then you also want to be really good at understanding what the protonation state looks like and what the deprotonation state looks like, specifically for any oxygen and for any nitrogen. When oxygen is deprotonated, it's going to have 1 bond and 3 lone pairs and have a negative charge. Nitrogen, whenever it's deprotonated, will have 3 bonds, 1 lone pair, and have no charge. Whenever oxygen is protonated, it will have 2 bonds, 2 lone pairs, and no charge. Whenever nitrogen is protonated, it will have 4 bonds and a positive charge. And the charges that we just calculated, that's just using the technique for formal charge.